Alright, hello everyone, April 29th. Alright. Been working with some LLM features, uptaking some LLM features, and I have a lot of bad things to say about it. I feel like somehow we don't use LLM the way that it's supposed to be used. I mean, from my perspective, generative AI, at least in its current stage, or probably in a very long time, is always just going to be 80-90% correct, right? It will never give you 100% correct stuff, which is one of the argument against LLM replacing programmers, because programmers has to be precise in the code, but LLM is never going to be precise because it's a probabilistic machine, and it's associative machine, right? Unless there is a paradigm shift on how these things work. As far as I'm concerned, it's always just predicting what's going to happen next based on what has been produced before, or based on what the prompt is, or whatever. Right? It's a probabilistic thing. So if the prompt is simple, straightforward, then the correct answer has a higher probability of being produced. But if your logic gets a little bit more convoluted, or like you start using a little bit more just some terms or phrases that doesn't appear very often in the training data, and then things just can go haywire, right? Really haywire. And the thing that I was working on is very simple. It's just summarize. Actually, I shouldn't say very simple. Summarization is a very hard thing, but we want to summarize. I'm going to give some logic to the summarization. We want to say, okay, if this happens, if that happens, then what's going to happen? But these if and else conditions is so hard to tweak. I'm not even sure how it can be done, but it's definitely not something that LLM is good at. So yeah, this is just my view. Like, if you want something precise, you have to code it. At least now, right? All those new AI tools, that Devon thing was pretty much just a scam. And all those tools that says that they can use AI to replace programmers, it's crap. It won't happen. It's not right now. Maybe in the near future, but I don't see that happening. On the other hand, if you just want, let's say, a summarization of a giant piece of text and you don't really care it to be 100% correct, you just want a general idea of what it's about, yeah, I think it will work. And videos, image, sound, music, and all those things that human perceive, it's okay. It's actually doing very well. Like all those videos that what's that Sora, right, created, it was wonderful, right? All those music that's AI generated, it passed because we humans, as we interact with the world, we are filling a lot of the gaps, right, by ourselves. So we allow the world we perceive to be not precise, right? You see the video, what it's 30 frames per minute per second, or whatever it is, right? If you're missing 1 or 2 frames, it's okay, right? It's okay. You can even miss, I don't know, maybe 20% of the frames, so we can still, we'll all see the image being a little bit bad, but well, we're okay with it. Yeah, that's just how we perceive the world. But that's not how computer perceive. Yeah, exactly. That's the misuse of LLM, is that we're trying to use it to satisfy a use case where we humans are not the consumer of. I shouldn't say it that way. It's just no. It has nothing to do with the consumer. It's just the expectation, right? Expectation. We generate an image, we don't expect it to be 100% perfect, because that's just how things are. It's never 100%, and we can fill in the gaps. We're happy with it. But if we want to say generate, a summary, and you cannot miss any data that's in the raw input, that's just not gonna work. Yeah, just some thoughts on this. All right, let's do today's things, and I only want to do one and then call it. All right, minimum number of operations to make array exclusive or equal to k. Zero indexed array. You can apply the following operations any number of times. Choose any element in the array and flip a bit in its binary. Flipping a bit means changing a 0 to 1 or vice versa. Return the minimum number of operations required to make the bitwise exclusive OR of all elements in the array equal to k. Huh. Okay. I wonder if we just exclusive OR everything first. Right? We exclusive OR everything first. And we check how many positions we need to do to make it equal to this, right? And every bit that you flip, so yeah, so in the result, if it's supposed to be a 1 but you got 0, that means we need to flip a bit, right? If we flip a bit, because now it's 0, if we flip a bit, that will become 1. If the answer should be a 0 or a 1, do you flip a bit as well? Yeah, I think you flip a bit. Yeah, it becomes 0. So isn't that just to exclusive or everything? Let's see this one. So 2, there's 1, 2, 3, 4. If we exclusive everything, that is going to be a 0, 0, 1. So we need to flip this to become a 0 and to flip this to become a 1. So we need to flip 2 bits, right? Which means maybe I just exclusive all. Yeah, 1 need to become. So which bits need to be flipped, right? So maybe I just exclusive all 1. This one give me 1, 0, 1. Then we see 2 bits need to get flipped. So is that just to exclusive for everything, including this, and then count a number of bits? I'm gonna do it that way. I have no proof at the moment. Just do it that way, and we'll see how it goes. Based on a 80% passing rate, I think that is the solution. We say int this equal to 0. Actually no. It should be k, right? For int n of nums, this one n. Count number of Java. Count number of bits in integer. Bit count. Integer.bit count. So we can return integer.bit count. This. Exclusive for everything, and count the bits in the final outcome. Each set bit represents one flipping operation. Yeah, that's why it's 80% passing rate. Okay, so this is done. I like to see this. So this is the Freedom Trail problem a few days ago, right? And I solved it by a BFS with a DP. Okay, so let's see the solution. Top down. Bottom up. Oh. Shortest path. With a heap. Okay, what is the I want to just read the code directly. Okay, so count steps. Try lock. Minimum steps between two indices of array. Try lock. Minimum steps. If key index. So this is where we finish, right? And for each occurrence, wait, hold on. Is this even the DP part? Yeah, this is the DP part. And this is the brute force, right? For each one, if it's equal to yeah, this is the current number of steps, and then we'll do the current one for the next, right? For the next total steps. Yeah, you go through every single one. If it matches the current, then we try it. If it don't match, we'll try the one that match, and then we go for, yeah, we just like, we try at every single round, we try every single one. Yeah. Okay, so with this, try lock, reindex and key, so best, if we reach the end of the keyword, it has been spelled. 0 steps. So given the ring index, given the key index, what is the number of steps, right? So for everything in this, so this is the same, right? This is the min step to reach. So given the current index in the ring and the index of this, so if I'm at this situation, tell me what is the minimum steps to spell it out, right? What's the minimum steps to spell it out? So I basically go through everything, right? I go through everything, and because for me, I go through everything, and if it matches, then I go it +1, and I will try the lock again from the next one, and then at the end, oh wow, this is actually very simple. I think the runtime will be the same. Dijkstra. This looks like mine, right? Because mine is a Dijkstra. Actually, no. This is the actual Dijkstra, which means you have the number of steps. Yeah, it is the number of steps to reach a certain target. And each time you want to pop out the shortest one. Right? Yeah, we are very close. It is a Dijkstra. Yeah, the minimal steps to go from this towards the end, right? What's the last one? Oh, total steps. if this continue, if we have seen this combination, so what we're trying to do is find out the total steps to reach the end, right? We start from this node. The node is represented by range index and the key index, right? We start from here and then we need to reach to a point where the key index get out, right? We need to reach a point of this, and at each point we need to find the minimum. So yeah, we start from here, and then we have the next step, right? We have the next step. So we go to its next step, or well, I know if it's equal, right? Because the next index is going to be the character indices, so the current key, right? The current key. The current key appears in these positions, so this is where we want to go next, right? This is the next index we want to go. But how do we go there? We need to push. We need to know the steps, right? And then the next index, because we go there, right? We go there. These are the next index we want, because we start from here and then we go to the next index, okay? And then among those, some has the smallest, so we push out the smallest and then we keep going. So the scene actually should be keep updating, right? You should keep updating the minimum, but it's the shortest path. So this is actually not really it is Dijkstra. Every time you pop up the smallest and then you go to the next key index, right? You go to the next key index, you get all these options and you push them in. Now you push them in, it goes to the next. And then, yeah, because it's, so the first time you hit, you reach an index, it's always going to be the smallest. But I still feel we shouldn't just use a scene. What I feel is you know the number of steps, so in here you need to check, right? Because this is to reach from the current node to the next node. I need to know if it's a better, right? If it's better, I push it in. If it's not better, then I don't even push it in. Yeah, these are just nodes. These are just nodes. Ray index and the key index are just nodes. This is from this position. What's the from this position? What's the number of steps? Right? What's the number of steps? And you move on, you have the number of steps, and each going on, you have a number of steps. So from this, and what we want to do is, yeah, this is very similar to this idea, very similar, but I use a priority queue, which I think is a better one. Because each time it come out is just minimum, it's the minimum number of steps to reach each node. Because of that, we don't have to keep a DP. Right? Because each time it pops out, that is the minimum number of steps to reach that combination. It cannot be even smaller. Each one is uniquely small. The first time it show up, that was good. So we just need to use seen. Very well. Yeah, I have a hard time. I didn't think about that DP, right? DP, because I try to be cute. I only want to move one step. I try to be cute. So that's why the DP didn't work for me. But in fact, if you just, indulge it, DP, right? I'm at this position. I want to go to the next position, right? I want to go know where I should go. So it goes through every single one, right? And you just DP that way. Okay. I think this one deserves another shot. I actually want to do this one more time, just by itself. I want to solve it using the DP method, and I want to solve it using the like a mixture of Dijkstra. Okay, I'll do this some other time. Yeah, I'll end it today. I'll see you guys tomorrow.